equal to 0, and the Maxwell wave equation implied that K must be a light-like for vector, right? So the question that was asked is, why can't A be parallel to K? Now, I've already actually discussed this in class. I've discussed it in two ways. One way is to go back to the fact that we can have a solution of box squared A equal to 0, which is a plane wave kind of solution. So the solution is, can you see this writing, all of you? If someone has a problem, please speak up because I can't see any of you now. So the solution is A equal to the real part of some amplitude, which is a constant for vector, times the exponential I times the phase, which is K dot X. So that's the solution. And so this thing, this K dot A comes from the transversality condition, as you know. Now here, what we can do is we realize that there are two linearly independent light-like directions. So we can put vectors K plus, a light-like vector K plus here along the X plus direction, and a K minus here along the X minus direction. And of course, at each point we have a real plane, an R2 plane attached to this 1 plus 1 dimensional spacetime. So we have, therefore, the transversality condition is then K plus dotted into A equal to 0, and that's the same as K minus dotted into A. Okay. Now we can choose these light-like vectors K plus minus to have the components K0, which is equal to mod of K, 3 vector K, and K, 3 vector K. And of course, this is then these K plus and K plus minus, so plus minus. So the K plus goes with the plus, the K minus goes with the minus, and you can see that each of these is, of course, then a light-like vector. You can easily show this, right? And therefore, as a result of these two conditions, what we get is K0 minus K3 vector, ordinary dot product into 3 vector equal to 0. That's from this one. And from this one, we get K0 plus K dot A equal to 0. And as a result of this, we get the two equations. So K0, A0 being 0 means that A0 must be 0 because K0 cannot be 0. K0 can't be 0 because K0 is the time component of a light-like vector. So A0 is 0 and also K dot A is 0. So obviously K can't be parallel to A. And this is obvious from here. That's one way of proving it. The other way of proving it, a more sophisticated way, is to realize that the vector, 4 vector A, can now be expanded in each of the 4 directions. So we have K plus times K minus dotted into A. This is a 4-dimensional dot product. Plus K minus dotted. This is just basically writing the projection operator, plus dotted into A. Plus, now these are the two linearly independent directions in the 1 plus 1 dimensional space-time, but we have R2, so I'll pick some vector R times R dot A. And the relationship between these basis vectors, the relationship between these basis vectors, this should be 4 vector, everything is 4 vector. Yeah? So these are light-like, K plus and K minus, and R is a space-like for vector. So this is space-like, which means that R squared is negative. Of course, this is the same thing as, so now we can define the physical part, projected part, is nothing but A minus K plus K minus dotted into A minus K minus K plus dotted into A. These are four-dimensional dot products. And therefore, you can see AP is nothing but R into A. R dotted into A. So this is like saying that this is exactly like saying that there's a projection operator, AB, which is equal to delta AB minus K plus A, K minus B, minus K minus A, K plus B. Exactly, which is something we discussed in class. So AP is R dotted into A, which means that AP squared, squared norm of this is R squared into R dot R A whole squared. Now R scalar product A, this thing will be some number, okay, can't be zero, obviously, will be some number, okay, and the square of that will be a positive real number, and this is R squared, so this is less than C. So the projected part of the vector potential is space-like. That is what we were going to say. So it's the same result, and of course it's orthogonal. So you can see from here also, just from the definition of AP, that K plus minus dotted into AP is equal to 0. Okay, so I suppose that completes the discussion of what we mean by a transverse electromagnetic wave. Okay, so let me just get out of this. Yeah, I'm removing it. Right. Yeah. So I would like to start from here because we were. It will take a little time. Yes. Can you? Can all of you read this file? This thing that is on the board, on the screen?
Yes, sir.
Okay. So what we were doing last time is that we were actually looking at S of phi equal to this. Okay. And so my computer can go off anytime. If it does, we'll try to rest for a minute or two and come back. Okay, my computer, this old computer has a problem. It might go off, but not right now, I suppose. Still okay. Right, so remember that the action we discussed was that of a free scalar field. It was called the kinetic energy term, and phi was a scalar field. And we did the variational principle on this action, applied the variational principle, and found this extra boundary term. And now the boundary term I chose to be a cylinder located at spatial infinity, with the cross caps of the cylinder being space-like surfaces sigma t equal to plus infinity, that is the final time, and sigma t equal to minus infinity, that's the initial time, plus the body of the cylinder, which is at spatial infinity, which is a time-like surface. So these two are space-like surfaces, and this is a time-like surface. And this particular property we discussed in class the last time. So you see, when we talk about ordinary classical mechanics variational principle, what we have are the initial and final time surfaces. The initial time surface, which is a space-like surface, every constant time surface is a space-like surface by definition. So this constant t equal to plus infinity basically means the final surface, and this is the initial surface. And in classical mechanics, what we do is we say that there are the variations of the initial surface and the final surface must be equal to 0. So we are putting the same constraint here. Now, if we do that, then since the boundary has three terms corresponding to each of these expressions, then out of those three, this condition implies that two of them can be set equal to 0, just because of this, because there's a delta phi here, Ea del A phi delta phi, and if delta phi vanishes, this whole integral on that surface will vanish. So these are hypersurfaces, these are three-dimensional surfaces. So on that space-like, on the two space-like hypersurfaces, the integral vanishes. So what we're left with is 0 equal to the bulk term, the term which is this, which was this term, plus there's one boundary term which is located at t infinity or tau infinity. And that is the one which corresponds to spatial infinity, mod x, mod 3x equal to 0. Now, this one will not die just by itself. What we have to impose are called fall-off conditions. Okay? So the fall-off conditions have to be such that because this involves, it's a time-like hypersurface in space-time, it involves a volume of integration. Therefore, we will have to ensure that these things fall off sufficiently rapidly. And you can see that actually this is mod x cube, this goes as mod x cube, let us say. And therefore, it is adequate that phi of x, so the phi of x, delta phi will fall at the same rate. So in fact, this need not be so fast. It is enough that this is square.
Sir, can you please repeat once more why we took that delta phi variation at the two boundary conditions to be 0?
What do you do in classical mechanics? Okay, first of all, I want to see
okay, sir, got it, yeah.
Okay, so I have a suggestion. Just because we're doing it online, I would like you to turn on your microphone as well as your camera when you talk. Okay, when you ask a question.
Okay, sir, fine.
I would also like to request those who, yeah.
So one comment, can you, sir?
Please, yeah, go ahead.
Can you provide us that that slides to us? That will be very helpful because taking notes in online exam.
I have just Akshay, the class has just started, man. Hang on, all that you'll get. Okay? Yeah. You'll get the slides. Don't worry. Yeah, but I would like to request people like Shakti Khaldar that when the class is announced to be at 10, why are you coming at 10:15?
Sir, I am trying from 10, sir. There is a power off, so I cannot connect my Wi-Fi, sir. So that's why.
So where are you, Shakti?
Sir, I am in Baripur.
I see. Okay. Fine, I understand. Okay, so then this is a Wi-Fi problem which you can't solve. Okay, fine. Go ahead. Right. Okay, so now coming back to this, so these fall-off conditions are something new that you have to impose on field theory. And we shall assume that from now on, okay, so there's a mistake I should correct here. If phi goes as 1 over mod x squared for large mod x, then this would be phi 1 over x cubed. And therefore, we find that, yes, it is indeed possible that this integral will vanish because there's a new numerator has mod x cubed. This is a rough estimate, of course. Denominator has 1 over x to the fifth. So obviously, we have this kind of a, it vanishes. And what we get, therefore, is the wave equation. Because if this boundary term vanishes, 0 equal to this, for arbitrary delta phi, for arbitrary variations of the scalar field, the equation of motion is box squared phi equal to 0. This is called the Schrödinger-Klein-Gordon equation, massless. Well, I'll come to the property of mass in a minute, but right now we are dealing with a massless Schrödinger-Klein-Gordon. People call it Klein-Gordon. I have a little problem with that because this equation was actually first written down by Schrödinger. Of course, Schrödinger wrote down the equation as an equation of the quantum mechanics of a relativistic particle. And he had problems with that. And when he asked Pauli, Pauli said, why don't you go to the non-relativistic case? And that's how Schrödinger apparently discovered the Schrödinger equation with which you are familiar. Okay, now to carry on.
One thing. Sir, over here in field theory, that means phi 1 by x type potential does not exist.
No, phi is not a potential. Phi is a field.
Sorry.
Yeah. So and the field. No, if you have 1 over mod x, you see, then that boundary term will not die for large mod x. Okay. That is why we require that phi must go at least as die as fast as 1 over mod x squared. So that's a condition. It's a boundary condition we're imposing on phi so that the variational principle can be used to derive an equation of motion. Okay? Yeah. So these fall-off conditions will change depending on what theory you have. So for various Lagrangians, various actions, depending on the nature of the boundary term, you'll have to impose a fall-off condition. But what I shall do from now on, just to simplify things, is that I shall assume that the fall-off conditions are chosen such that the boundary term does not contribute. And therefore, I shall not discuss the boundary situation much from today. So today is the only time I'm discussing the boundary term. Whoever has missed this discussion, sorry for them, because I shall not repeat this discussion. But of course, you'll have access to my notes, as Akshay was saying, and you can have a look at them. Okay, so now going back to this, I now wanted to talk about making the action a little more complicated. So I said that this first term, which we introduced the other day, is called the kinetic energy term. This is sort of an analogy with non-relativistic particle physics. Non-relativistic particle mechanics, this is an analogy. It's not really kinetic energy, but everybody calls it kinetic energy. So it's a name. And then you can add a term which is minor v of phi. And this is again called the potential. It's called the scalar potential. It's not really a potential. Because you see, when you think of a potential in classical mechanics, the potential is usually a function of the coordinates, the generalized coordinates, which are non-derivative. There are no q dots. Usually that's the kind of potential we deal with. Here also, v is a function of phi. It's a non-derivative. There's no derivative of phi in this expression. But it's called a potential, again, in analogy. But remember that v of phi, when I say it's a function, how many variables are there? Actually, a continuous infinity, right? Because phi itself involves a continuous infinity of variables, one variable for each space-time point. And because I'm integrating over entire space-time, there's an infinite number of variables. So when you call potential, I've included these inverted commas to signify that it's just a name. It's not a potential like in classical mechanics. So it's not like the Coulomb potential or anything like that. But I've given some examples just to clarify. Here it is. One example is v of phi is half m squared phi squared. And that leads to the equation of motion, which you will have to verify, box squared plus m squared phi equal to 0. And this is not the massless, but the full Schrödinger-Klein-Gordon equation. That's the Schrödinger-Klein-Gordon equation. This represents a field with this property, which I shall call mass. Now, what does a mass for a field do? You're all familiar with the mass for a particle or a bunch of particles, each carrying some mass. What is the meaning of a mass for a field? Okay, so that's the next page. Right. So here I repeated. So here it is, the Klein-Gordon equation. We call this the mass term in the scalar potential. Now, why do we call it a mass term? Now look at this equation. If you make a Fourier transform, you get minus k squared plus m squared phi tilde of k equal to 0, right? That is easy. All of you know that. And that would mean, because this can't be 0, k squared is equal to n squared. Now this is a condition we are familiar with. Well, actually, mistake. I should have put a c squared here. Let me just put a c squared here. Units. See, the problem is we always deal with units when we do field theory, units such that c equal to 1, and that habit somehow continues. So actually this term is m squared c squared. So this c squared, at your age, you can't afford to miss the c squared. When you come to my age, you can afford to lose the c squared. So this is k squared equal to m squared c squared is like, for a particle, it's p squared equal to m squared c squared. So k is like the momentum, momentum of a particle. What is k? K signifies the Fourier mode of the field phi. So the Fourier modes behave like particles of mass m. So this is one way of saying that you have a field which has a mass m. A field has a mass m if its Fourier modes are like momenta, momenta of a particle living on the mass shell, the mass hyperbolon. Okay, so that's really what this is. Now, before I go to this case, let me go to the other case. So this was A. B, I shall talk from here, and then C, this will be C. So before I come to B, let me talk about C. So C is slightly different. So I will have the mass term, m squared, c squared, phi squared. But I shall now add a source term plus j phi. Now you see v of phi has to be Lorentz invariant because it's a part of the action which is Lorentz invariant. This term is obviously Lorentz invariant. If phi is put in, phi is a Lorentz scalar, then there should be a source which is a Lorentz scalar as well, this j. Okay? And this leads to the equation. Again, you have to work this out. Box squared, so there's a c squared. I'm missing the c squared always. I'm going to be very sloppy about powers of c, and it will be part of your task to make sure that I'm right. Minus j. Okay. So this is the Klein-Gordon equation, the Schrödinger-Klein-Gordon equation for a scalar field with mass m interacting with an external field, external source or external current source. Current. Okay, so that's the other situation because you're familiar with the Maxwell's equation. So you have some box squared on the left hand side and a current on the right hand side, the source. So the source generates the field. Now here, coming to C, we see something totally different, something of which you have not seen any analog yet. So I choose a kind of potential which is the mass term plus a lambda y4 factorial phi to the fourth. Why am I choosing only even powers? What about odd powers? Well, I'll come to that in a minute. But if you do work out the equation of motion, the field equation, you get this. Okay? So now look at this equation. First of all, this equation, that equation, etc., were linear equations. So when the action is quadratic, is a quadratic functional of the field phi, then the equations of motion are linear. They are more like Maxwell equations. But if v of phi has this funny form, then we realize that this equation is nonlinear. It's a nonlinear partial differential equation, which means that the sum of two solutions is no longer a solution. A nonlinear partial differential equation has this property that it does not obey the superposition principle. So obviously such an equation cannot be useful excuse me, cannot be useful for electrodynamics, which we know is a linear theory. But I'm just commenting it because I'm speaking in more generalities, not just electrodynamics. So the point is that this is a nonlinear term, which means that if this equation is true, the physics will not obey the superposition principle. The other property here is that if you compare the two, which is why I did this first, then this term, the nonlinear term on the right-hand side, tells you that phi is its own source. Now, this is also something quite different because so far, whenever you've had to deal with sources, you've always dealt with sources in which the source was an independent external variable. Here, it seems that the phi is in self-interaction. So the dynamics of phi is being generated by this nonlinear self-interaction. So this self-interaction is a property of field theories which you do not see in particle physics at all, particle mechanics. It's a new kind of physics. It's an absolutely new physics, and there's terrific things happening. Now, I should tell you that when we look
so
at...
Can you explain the self-interaction again?
What exactly? No, you have to ask who is, first of all, whoever is asking a question has to... Akshay.
Explain the self-interaction.
No, what do you want to know? First of all,
it's not clear to me why it is called self-interaction.
Because the source is made up of the variable itself, you see. That is why it's self-interaction. The dynamical variable phi is interacting only with itself. There is no external current like in B. In C, phi is interacting through this cubic term only with itself. Okay, Akshay?
Okay. Sir, can you give any physical example of any sort of natural phenomena which does
No,
this?
well, I can, but these are uh, beyond what you've been studying so far. Yes, it does happen in dense materials. In dense materials, in certain kinds of dense materials, the susceptibility may be a function of the electric field. And you can expand the susceptibility in powers of the electric field. If this is the case, you realize then that the Maxwell's equations will have to be changed and some new nonlinear interactions of the electric field with itself will have to be included. Now, these are real. These nonlinear interactions have been identified, it's real, but these equations are very hard to solve, unlike the standard Maxwell's equations in vacuum. Okay? So there are examples of this, but we shall not worry about those examples because we deal with vacuum. We don't want to deal with dense materials. But there are such materials which have this property. Now, on the other hand, since you ask, I should tell you that in particle physics, there are loads of examples. The Higgs boson, for instance, is such an object which obeys an equation of this type. Okay, so is the other non-abelian mediating particles known as gluons, W bosons, Z bosons, and so on. They all have self interactions. So there's a huge galore of self interactions in particle physics. So when you study particle physics, this will no longer be something exotic. It will have to be there because if it is not there, you don't generate the strong and the weak interactions at all. Is that all right?
Sir, one more thing. Sir,
Yeah.
in particle physics, we deal with particles. Why I don't know, means why field theory is coming over there?
Yeah, the word particle physics is in some sense a misnomer because we think of particles as excitations of fields. Again, I can't go too much into this because it's not this subject. But in particle physics, particles are excitations. You know, excitations meaning just like you have in hydrogen atom, excited levels, energy levels. In particle physics, you have a field, you have a quantum field, and the excitations of this quantum field are particles. Okay, so we talk about particle physics, but actually we should call it field physics. But I didn't choose the name, you see. It's a name I'm just following. All right? Is this okay now?
Okay, sir.
So right. So already we have seen some fantastic new things happening. Okay, which we did not anticipate. I mean, so we have discussed. Excuse me. We have discussed a new concept of mass of a field in one particular way. We have, of course, talked about an external source, which is not new because we have dealt with such sources in the context of the Maxwell equations, and we'll continue to do so. We have also dealt with this phenomenon of self-interaction for a scalar field, but you can also have it for vector fields, tensor fields, and so on. But we are keeping the discussion as simple as possible so that we don't get cluttered by the mathematics right now. Okay? But the ideas are very clear that there are, whenever you go from classical particle mechanics to classical field dynamics, new things happen. So there are new things that are happening. So that was the idea. All right. So now I hope that all of you will do your shada khata and work out these equations so that you don't have a problem. And I'm going to assign maybe today. I have to make up the problem sheet. So what assignment number are you at? You've finished one assignment, right?
2 assignments.
So let me ask the class monitor, who is Shomona. Shomona, hello, are you there, Shomona?
Yes, sir. We have completed 2.
So how many assignments have you completed? One or two?
Say 2.
Two. So you've handed two assignments to Oditropal, right?
Yes, sir.
Okay. So assignment 3 is going to be on the way soon. Okay. So right now, this has all been basically, you know, this has all been kind of whetting our appetite to begin with, appetizers. And now we shall come to the main thing. We shall come to writing down an action, first of all, for the free electromagnetic field. How do we write down this action? Well, what we know is that so S max is equal to integral d4x L max. Now, L max is a Maxwell field Lagrange density, and that has got to be, I'm simply writing it like this, A and del A. I'm not putting indices or arrows and so on. So it has to be a function of the vector potential and first order derivatives, space-time derivatives of the vector potential. So that's the kind of expectation we have. The other properties is that this Lagrange density must be Lorentz invariant. It must be a Lorentz scalar. So will have to be Lorentz invariant. Second of all, it should also be gauge invariant. So let's make a list of this. So property 1, Lorentz invariant. Well, these are expectations which we have. And 2 is that it must be gauge invariant. We also know from our experience that it's invariant under parity. Invariant. By that I mean that if I change my spatial coordinates to negative of themselves, then the Lagrange density must not change. So these are the kinds of things that restrictions that we should like to impose. And then we begin to think, how do we implement them? Well, actually, we have done this problem. And the problem goes back to the problem of looking for field bilinear invariance. Remember this now? We did this in class. What are the field bilinear invariants? I would like to ask. Let's see. Now I shall call upon Shafak. Shafak, are you there, ma'am? Shafak? Hello, Shafak. Can you please unmute?
Yes, sir. I was. Yeah,
Good.
just a second.
Can you tell me what are these bilinear field invariants? Don't look at your notes feverishly. Think. Use your head. The giveaway is bilinear. So the way you have to think, Shafak, is without looking at notes. What does bilinear mean? Bilinear means that it must be two quantities, right? Bi means two. And the field, the electromagnetic field, we have always been talking about in terms of a certain tensor. You remember that tensor?
The
F tensor, yes, FAB. But FAB is a tensor. FAB satisfies this property, but not this property. It's not Lorentz invariant.
LAFAV.
Well, that's also not right. But this word tells you what you should construct.
Another FAV.
Another FAB, exactly. So that's one bilinear invariant. And wasn't there an assignment in which you were asked to compute this quantity in terms of the electric and magnetic field intensities, E and B?
So this quantity.
Okay, let me see somebody else wants to answer. So Shafak, do you remember what this was in terms of E and B?
So this. I know.
Okay, go ahead.
FAB, the field tensor, it has the components like the, I know it has, how the tensor looks like, I know, but how the product should look like, I'm not
Yeah,
sure.
this is a contraction, right? FAB. So you have to sum over AB. And what you get, okay, so let me ask
Square term.
maybe someone else. Let's see. Srija, would you like to answer? Would you please turn on your camera, please? Because I have no. Srija Ghosh. Where is Srija? I can't even see her. She's vanished. Maybe I should ask Oritri. Oritri, can you say what this is?
Yes, sir.
Yeah,
That
so,
FAB term.
yeah. If you write
Okay.
it in terms of E and B, what do you get?
E square minus B square.
Yeah, it's proportional to that.
Yes,
Actually, it
proportion.
turns out
It's
to be.
actually E square by C
It's
square minus B square.
no. We are into now. We are into Gaussian units.
Yeah.
So it's
So
proportional to B squared minus E squared.
minus E square, right? Yeah.
E and B have the same units, so it's proportional to B squared minus E squared. But Oritri, can you answer? Is this the only bilinear invariant, or is there another one?
There is another one.
What is that?
F star AB and then F
Very
F
good,
AB.
very good,
Yeah.
very good, very good. So you are saying something like E A B C D, F A B F C D, right?
Yes.
And what is this in terms of E and B?
E dot B.
Ah, very good. Up to some number, it's proportional to E dot B. Okay,
Right.
good. Thank you, Oritri. Let's see. Now I want to ask Srija if she shows, but Srija, I can't. Maybe Katha. Katha, can you tell me?
Yes, sir. Yes, sir.
So out of these two invariants, both are scalars, right? Obviously, both are
Yes.
scalars because of this construction and this construction. They are scalars. But is there any difference under? So we have scalars. We have gauge invariants because it's constructed out of F. The question then is parity. Okay? Do they have the same parity? Do you think they have the same parity? Yes, Katha. What is your answer?
No, sir. They don't have the same parity
Because
because I think if AB, that is B square minus C square, if I change x to minus x, then B square minus C square remains the same. But
yes,
for the
very good.
but
So
for
P
the case of
invariant.
E,
Yeah.
yes.
Yeah.
But for the case of E dot B, then if I change x to minus x, E changes from E to minus C,
Yes.
and B changes from B to B.
Very good. So this violates parity.
Yes, sir.
Good. Thank you. Thank you very much, Katha. That was excellent. Excellent answer. Thank you. And therefore, ladies and gentlemen, friends, you realize that we shall have to ask the question, does the Maxwell-Lagrange density violate parity or not? What is the physics? What is the observation? What is the experiment? What do experiments tell us? Okay, that is the key question. And that question, of course, cannot be answered by theory. So experiments, observations, tell us that L max must be is parity invariant. So you see, we have now made a choice out of these field invariants. So we can say that L max is proportional. L max can be proportional to FAB. Okay, but one can say, sir, why not this to some power n, where n could be 1, 2, 3, 4, 25, 420, anything. This is also true. This is acceptable. But the only reason we choose FAB is simplicity. We realize also other things. For instance, if you chose this to be not 1 but 2, if you chose this to be FAB squared, and recall that FAB can be written down in terms of the vector potential like this, right? This is the formula, this is something we have discussed endlessly. Then this term, this quantity will tell us that if you now put in a higher power, then the equations will be higher order in the derivatives. But because you can see here itself, we have linear orders in derivatives in the f's. So if you put a higher power, then there will be 4 derivative terms. So when you look at the equation of motion, you might get a 4th order equation. Now, normally, when we do classical mechanics, we always restrict the Lagrange density, the Lagrangian, to be a function of the generalized coordinates and their first order derivatives. The reason we do that is because we don't want to end up with an equation of motion after doing the variational principle, which is higher order. Now, why we do this should be known to you. It has some very deep significance, some very deep analysis. The short answer is, if you take higher order equations, you get higher order equations, then their solutions require a larger number of initial data, and even so, they may not be uniquely determined. By that I mean, if you consider, let's say, any equation which is like x double dot or x triple dot, then when you solve the equations, then you find that there's an ambiguity in the way these things evolve. So there are deep theorems of classical mechanics which tell you that you're safe when you deal with n equals 1. So this one we avoid. We go back to n equals 1. So this is our choice for the Lagrange density. Simplicity criterion, of course, but it's also the fact that we want second order field equations. Okay, now for in Gaussian units, the Lagrange density for the Maxwell field is chosen to be 1 over, I think, 16 pi c with a minus sign, okay? FAB. Now, if this is the only term in the Lagrange density, then you realize that this constant, so then the action S Maxwell is equal to minus 1 over 16 pi c integral d4x FAB. Of course, any multiplicative factor in front of the action, if this is the only term in the action, then this multiplicative factor is actually quite irrelevant. But I'm just putting it in because eventually we would like to couple it to an external source. And then we know what the Maxwell's equations are, and we should get back those same Maxwell's equations with the right constant in front of the current density. So in anticipation of that, this is sort of a hindsight thing I'm taking this to be the result, okay? So let us now write down this in full glory. Well, remember that the action is a functional of the dynamical degree of freedom, which for us is the 4-vector potential, and this is minus 1 over 16 pi c integral d4x FAB. So now we want to make a variation and see if we do indeed get, right, the homogeneous equation of motion for A, the homogeneous equation of motion, which we know. We can talk about projections, etc., solutions later on, but right now, the variation. So delta A S max must be equal to 0. And now let us see this. So you see that this is like a square, FAB. This is a contraction. So when I do a variation, I will get a factor of 2. I'll get a factor of 2 because, I can do a delta FAB times FAB, but I can also get F AB delta F upper AB. But this, then I can always interchange the up and down indices, and therefore I get a factor of 2. I push the indices down here, I push the indices up there, and therefore this is a unique result. Delta FAB, delta FAB. You can also write the delta on this one, but it's the same result. Okay. Now what I do is I notice that this is further equal to this quantity. Delta del A AB minus del B AA FAB. I've done it with the delta part. Okay. And this part, you see, I can rewrite it as 1 over 1 minus 1 over 8 pi c integral d4x. I can interchange the derivative okay, and the delta, the variation. But notice that here, these two terms are identical again. Why? Because I can change B to A to B, and put a plus here because this is antisymmetric, right? So only the antisymmetric combination will come, and therefore what I have here is this very simple term, which is 4 pi c. 4 comes because these are identical terms. If you interchange A and B, these are dummy indices, so call B A and AB. But then in the second term, I can write FBA equal to minus AB, so this minus and minus will give me 2 identical terms. Okay, so this is very simple stuff. Del A delta AB times FA. Okay, and then okay, now I want to extricate the derivative from the delta, from the variation. So I push the derivative onto this guy and ignore the boundary term, so this becomes a plus, and I get delta AB del A FA plus boundary term, which I'm ignoring. By our boundary conditions, which I have discussed earlier. So now we have this term, we have a delta AB. So for arbitrary infinitesimal variations of A, the 4-vector A, this will have to vanish, which means I get my Okay.
Sir,
Yeah.
sir, sorry to interrupt. Okay, I'll just come in here. Sir, I could not understand why there is a sign change. That was a
Now
bit.
I can't see who is talking, so unless I see who is talking, I will not answer.
Oh, okay, sir. My camera. There is a problem with my camera. Just a second, sir.
Who are you?
Sir, Rahul, sir.
Huh?
Rahul, sir.
Rahul.
Yes.
Rahul. Yeah.
There's a,
What's your
there is
problem,
a problem
Rahul?
with my camera. So
Okay. Get your camera fixed. So what is your problem?
the problem is, sir, I cannot understand why there was a sign change with 1/4 pi c. That was it.
Rahul, do you remember your integration by parts which you learned as a child?
Oh, okay. Yes. I
That's all
remember.
I've
Yes.
done.
Okay,
I've
okay,
flipped the derivative from this guy to this guy with a
okay.
boundary term which I argued to be zero because
Yeah.
it's because of this integration by parts. There's a
Okay.
boundary term which is the integrand. So u dv is always, uv, which is a boundary term, minus v du, and that minus sign kills this minus. Okay?
Okay, sir. Understood. Thank you.
Right. So that's done. And now, okay, so we are done then. This is indeed the equation, and if you want to write it in terms of the A, we know what that is. This is box squared AB minus del B del A equal to 0. And that was the starting point of our discussions earlier, but now I have fulfilled my promise to you that indeed I can derive the Maxwell equations, okay, from an action principle. So if there is a question about this entire procedure, I will take a minute, okay?
Where
I
is
would like to
J?
hear.
Where is
J. This is the homogeneous equation. So this I call Maxwell because it's pure Maxwell. So this is the action that I wrote down was for a free Maxwell field, right? And we did also look at this case when we discussed the Maxwell equations. So this is that case, the free Maxwell. So the question then you've asked is the right question. Okay. How do I then include a source? Of course, that will have to be an extra term in the action. So the pure Maxwell, so at least before I get to that term, is this clear how the pure Maxwell equations come about? Is there any question about that? That is my question. Okay? Right. So now let us discuss how we can introduce a source. You see, we have actually already done that. So let's go to the next page. We've already done that because remember when we introduce a source term as source, in the case of the scalar field, this was a functional of phi and j. And remember, we simply wrote down integral d4x jx phi x, right? So it meant that since the Lagrange density has to be a scalar, phi is a scalar, so the source j for a scalar field must be a scalar field, must be a scalar current. And that is why this j here is a scalar current. For the case of the scalar field. What about the electromagnetic field? It must be a function of A and some J. So to anticipate, well, what can it be? Again, there is a simplicity criterion. So what we do is we write J as a vector because our degree of freedom is A, which is a 4 vector, to get a Lorentz in a 4 vector. So J here is a space-time vector current source. we know what the components of J are, the charge density and the current density and so on. And there's also a constant here, which I always forget. So I shall ask you to fix this constant. But there is a question here. And is this obvious to you that this quantity is gauge invariant? Because remember, we write involving the electromagnetic vector potential or vector potential in the action. Write down as an action must be Lorentz are guaranteed in vector, and J is a vector, space-time vector, space-time vector. So that's guaranteed. But what about gauge invariance? Because there's only an A here. So let us check that. Let us only check the J dot A term. So if you have the integral d4x, so when we go to a different gauge, we get d4x J A omega. What is A omega? So that's a gauge transformation, right? What is this quantity? So let me put in indices. So let's say that this is JA and this is AA plus, remember the gauge transformation of A, it's the bold vector potential plus the forward gradient or just the partial derivative of some arbitrary function omega, arbitrary scalar function omega. That's a gauge transformation. So let's look at what this new term does to us. So the first term is the same as before. The first term is again J dot A. But what about the second term? Right? So that is a key question. If this term were to remain, then J dot A would be a bad choice because it will not be gauge invariant. But on the other hand, we have, so I'm only now looking at this term because that other term, this is a term we already have. So this term, on the other hand, I can partial integrate, throwing away the boundary term. If I do a partial integration, I get del A Ja times omega of x. But then if this is 0 as an equation of continuity, then I have no problem. So what we are saying is this term J dot A is gauge invariant provided the current is conserved. If the current is locally conserved, that's del A J A equal to 0, then I have no problem. The gauge non-invariant term drops out, and indeed I have a gauge invariant action. Okay? So now the task is to pick an action S, which is equal to the S Maxwell plus the S source. In the S source here, I have left a constant to be fixed by U. And you're going to do that so that I get the equation del A FAB equal to 4 pi by C GB. Fixed constant, fixed constant. Can you not do that? Can you not do that? It's probably minus 1 over C squared or some such thing, but you're supposed to do that. Okay? Because you know that I've already given you the constant for the Maxwell field, and now you realize that that minus 1 over 16 pi C is very important. If you did not have the minus 1 over 16 pi C, then you won't get this constant right, which we need in order to get our Chotobelar, the Maxwell equations we learned when we were very young, maybe last year or something. Okay, so in order to get that, you have to fix the constant. I leave that as a simple exercise for you to fix the constant. Okay. Now, before I go on, I'd like to show you something. Um, although I have argued that okay, so now last time it was Rahul or who was it asking about J? I forgot. Was it Akshay? One of you were asking about putting in a J, and you can see that the J has been put in with great ease, and the variation has led you to an equation of motion, which is actually very simple and the expected one. So you see, the action way of getting to the Maxwell's equations with all the sources is actually quite easy. There's nothing to worry. And I hope the person who asked me the question about J, I forgot who it was, is now satisfied. If not, please do stop me and ask the question again. Okay? Is that all right? Okay. So this is where we are. And I wanted to show you something. I wanted to show you that if you chose your Lagrangian L prime, let us say, equal to some constant lambda times FAB, something that people mentioned, Shafak mentioned and others mentioned, FAB, Katha mentioned, FAB star FAB, right? Of course, we ruled this out on the basis of parity. But let's write down the action corresponding to it as prime, because I want to show you something about this. So this is lambda d4x E ABCD FAB FCD. And you can write the same thing as prime like this. Okay, lambda integral d4x E ABCD. So I can put in a 2 factor because FAB, although it is del A AB minus del B AA, there's an antisymmetry between A and B. So I can just say 2 del A. So I take one of these guys, AB, FCD. Okay. Now, this one, on the other hand, I can rewrite as, now this is the key part. Why can I do that? Because you see, the term which is the deficit term, the term which I am not writing down, is actually 0. Because EABCD del A FCD is 0. That's exactly the Bianchi identity. And the reason it is 0 is because FCD, if you were to write down FCD as del C, AD, etc., there are two derivatives del A and del C which are symmetric in under interchange of A and C, whereas this quantity is antisymmetric. So this is now this. And therefore, what we have seen is that if we chose that action, if we forgot about the parity argument and still chose the other bilinear invariant as our Lagrange density, the action is a total for divergence of a vector. This is a vector, and this is the total for divergence, and therefore this is just a boundary term. Therefore, this will vanish by fall-off conditions. Boundary terms vanish. So the boundary terms vanish by fall-off conditions. Now, there's a little trick here. There is no delta here, there's no variation. So what we say is that the way that the cross caps, the sigma plus and sigma minus, we say that this is, after all, a Ford divergence, and therefore you know from Gauss's theorem that it is then a flux over the field, but the flux going inward and the flux going outward will balance each other out, because you see the flux here on the time-like part of the surface is the flux is always outward, whereas the normal to that surface. Sorry, the normal is always outward, but the flux is always going into that surface. So whatever flux is going in will, at sigma minus infinity will go out at sigma plus infinity, and you'll be left with 0. So all four divergences, integration of four divergences from now on is a boundary term which we drop. And it is because, so when you get a boundary term, what that means is that there is no dynamics in the bulk. The dynamics, if at all, would be there at the boundary. And if we impose the fall-off conditions, then there's nothing at the boundary. That's the kind of boundary condition you're imposing. Of course, you can choose boundary conditions in such a way that that does not happen. You can make your life miserable. You can also make your life miserable by thinking of a room. In a room, the fields do not fall off to 0. So you have to impose other boundary conditions. And then this trick which I'm talking about will not work. Okay? The boundary terms vanish only when you consider the boundary at infinity. Only when you consider the boundary of the entire space-time, then the boundary terms vanish. If you choose a finite region and look at the boundary of that region, then of course it is not 0, and you'll have to augment this Lagrangian, augment the action by a boundary action, such that variation of the bulk action compensates the variation of the boundary action. That's another ball game. We should not consider this. So in the simple context that we are talking about, we have this possible situation now, that indeed we have this beautiful thing. Okay. So now we are in a position to go back to, so what we have done so far, you see, in our little venturing out into the field theory, classical field theory, is that we have discussed classical scalar fields and we have discussed classical vector fields. So a couple of things to notice here. One of the questions which I would have expected is that why not add a mass term? Good. So let's consider that situation. It's a very important question. A lot of students ask this question, and perhaps it's because it's an online thing, it's difficult for you to ask questions. But let us go into that anyway. Okay? So the question that I'm asking is, why can't we add master to Lmax? So what's a master? Well, let's say we have a master, Lm, equal to like this, half, just like the scalar field, we will try to write it like this. Well, actually there's a minus sign, but let me not worry about it. AA. So this is, it's just like the scalar field master, scalar mass, that was half m squared, phi squared, right? So we are trying to mimic that. It has to be AA in order that it's like phi squared. So there's, again, I forgot my c squared. Pardon me, there's a c squared here, which I forgot. So can we add a term like this to the Lagrange density? So I will forget the source term now because that we have already mentioned. So we can have a Lagrange density which is L max plus Ln. And so the actions also will be S equal to S max plus Sm. And that should lead to an equation of motion, box squared AB. Actually, it's very easy to write down in another way. Again, I'm not deriving this action, it's left as a home task, box squared plus m squared, ma squared, AB minus del B del A equal to 0. So that's the equation of motion if you take this. What is wrong with such an equation? Why aren't, by the way, a man who first worked on with this kind of an equation of motion goes by the name of Proca. He did actually look at this equation. But what is wrong with this? Photons. If this is going to describe photons, then can photons carry mass? That is the question. Can photons carry mass? So to answer that, let us go back here. Can I write down this equation consistent with the three properties which I listed, I think a couple of pages back, maybe 4 pages back. Yeah, right here. So these are the three properties. Do we have Lorentz invariance? Yes, we do. Do we have parity invariance? Yes, we do. Do we have gauge invariance? Well, let's see. So the question that we want to ask is, if I write down a mass term like this, do we have gauge invariance? Is this term gauge invariant? So let us look at L prime M, which is the gauge transform part of this, which is half. We already know that the Maxwell action is gauge invariant. We won't worry about that. So Lm, the mass term, is it gauge invariant? That's the question we are asking now. So this will be AA. Oh, sorry. Wow, we have a problem, sir. This is not equal to Lm. So this is not gauge invariant. So we now have one of the great properties of nature from this very simple consideration. We want our theory to be gauge invariant because a choice of gauge is like a choice of coordinates. It has no physical significance. So whatever Lagrange density or action we write down must be gauge invariant. But this excludes the writing down of a mass term for the Maxwell field. So if you look at the Proca field, you can't treat the A there as a Maxwell field. It does not, this equation of motion, this action is not gauge invariant. But then Proca would say, look, I'm not talking about the electromagnetic field. So why are you pushing me with the property that it is not gauge invariant? I don't care if it's gauge invariant or not. Good. Good. But there is a huge number of things related to this, and I'm going to say a few things which are fairly physical, no more math. So what we realize is that the Maxwell field cannot have a mass term, unlike a scalar field, because such a term will violate gauge invariance. Now you might say, well, why not something more complicated? Can't I have a mass term which is more complicated? Then is that a mass term? Because a mass term, remember, must be quadratic in the fields. If this is going to be quadratic in the fields without a derivative, then that's the only thing you can have, right? At least a quadratic Lorentz invariant object, AAAA, which is A squared, the 4-vector squared, that's the only possibility you have. Okay? If you write a higher power of A, that is not a mass term. That may be some self-interaction term, like a 5/4 term. That's a self-interaction term. We are not interested in that. We are asking about a mass term. And a mass term is precluded in the Maxwell theory by gauge invariance. This is very deep. This is very deep. So you can't write down anything for the Maxwell action. The Maxwell field, the Maxwell vector potential has got to be a 4-dimensional space-time vector, 4 vector, okay, which is massless. So A is a massless 4 vector. And we don't know what that means. Okay, so that's great, because just from a basic principle of gauge invariance, which everybody believes in, you are showing that the Maxwell field must be a massless 4 vector. It cannot possibly allow a mass term, unlike a scalar field like the Higgs field, which allows for a mass term, because there is no concept of gauge invariance here. In the case of electrodynamics, we have the notion of gauge invariance, and that rules out adding a mass term. But this is something fairly deep. And it's so deep that this continues. Because I told you, remember, I told you that there are these other fields which mediate the strong and weak interactions. Okay. The strong and weak interactions. You see, the range, this is now kind of loose. I'm going to make some loose statements. So the range of a force is proportional to 1 over the mass of the mediating particle, mediating field, mediator. 1 over the mass of the mediator. So when you have a mass term like this, the force due to the scalar field will be 1 over m. Okay, the range of the force. On the other hand, what we know for sure is that the range of electrodynamics is basically long range, is infinity. And therefore, that is consistent with the fact that the mediator, which is the vector potential here, must be massless. Okay, so this is electrodynamics. The electrodynamic force, the electrodynamic interaction goes over very, very, very long distance. It's a long range force, and therefore the mass of the mediator, I have not proved this relation, I have only pulled this relation out of quantum field theory. The way to show this would be done later on. But if this is true, then this is consistent with the fact that electrodynamics, being a long range force, couldn't possibly have a mediator field like a photon field or the electromagnetic vector potential, which carries a mass. The mass must be 0. Of course, this is not our argument to put the mass term to 0. The mass term is 0 because it's not gauge invariant. So you see now, gauge invariance is telling you that the electromagnetic force must be a long range force. It's really, really beautiful how all these facts come together. Okay? All these facts come together. However, there is a question here. Is the strong interaction long range? The answer is no. Is the weak interaction long range? The answer is no. We exactly know what is the range of each of these fundamental interactions. The two long-range interactions are electromagnetism and gravity. And the two short-range interactions are the strong and the weak interactions. However, they also have different ranges. They are short range, much shorter than electrodynamics or gravity, but they still have different kind of ranges, finite ranges, okay, but very, very small compared to our length scales. So it will be in the nanometer and so on, nanometer range. Okay. Then the question is, so are we saying that the Prof field, which corresponds to this, there is a great approximation to describe the strong and the weak mediator fields? To the fields which mediate the strong and weak forces behave like a Prof field. And this is the whole thing. This is the whole thing which people have been struggling with for generations, because a lot of people felt that yes, they have to be like a Prof field. In fact, Prokaf's idea of working with this field came up because he was trying to describe a vector field which will mediate the strong and the weak interactions. That was his motivation for working with this equation, the Prokaf equation. Except that it doesn't work. It doesn't work because I'm not at liberty to tell you these things, but you can probably see that, you see, when you have an equation like this, the A field cannot be transverse, there is no transversality condition, and because of that, you have problems. You don't have wave-like solutions and so on. So there are issues there. But let me not get into those issues now. The point is, this does not work for the strong and the weak fields. And then what works? So this is where I shall not tell you any more, except to say that this is what Mr. Higgs discovered, for which he was awarded a Nobel Prize. He found a way. He found a way to maintain gauge invariance and to give vector fields a mass. So you see, this is exciting because he's not using this property of violating gauge invariance by putting in a mass term. That would be too dumb, too stupid. Higgs was very smart. He came up with a way of avoiding that problem. You see, that is the genius of Peter Higgs. And if I have time in this course, I shall tell you how he did it, because I can tell you how he did it. It's not something, I can tell you the basic mechanism. I can't tell you about strong and weak interactions, but what is the basic physical idea? How does the math work? That we can discuss. Okay, so you see, this masslessness, and gauge invariance, Broca field, all these are connected very beautifully. They're all connected very beautifully. But there was a question which people asked me, and that was a slightly different question. So I shall end with the question. I don't have time because it's already almost 11:30. So does charge conservation result from a symmetry, from a Noether symmetry? So obviously, I'm preparing the ground for this great theorem, which many of you may have seen in your classical mechanics class, maybe all of you have seen, that if the action has a symmetry, then there is a conserved current and a conserved charge. This is the theorem known as Noether theorem. So, apart from questions and so on, discussion on what we did today, what we should continue from next class, from, Friday is, Thursday. We have a class on Thursday, right? So anyway, today my computer did well. So you must all clap for the computer, for my Buddha computer. Okay? All of you give a clap. Unmute and give a clap for the computer, not for me. Yeah, so clap. Clap for the computer because, thank you. Computer says thank you. Yeah, okay. No, you're not applauding me, by the way. You're applauding my Buddha computer, okay? Right, okay, so today, this is it. And
Sir,
we shall, yeah,
sir, I
you have
have
a question?
not a question. On the thing is, what book you will suggest to read this classical theory of which is pretty interesting.
Classical theory of fields. Classical theory of Landau. But let me tell you the Landau notation, Landau way of dealing it will be somewhat different from mine.
Therefore I was facing the problem. So can you
there is no book. I'm not following a book, you see. I'm not following a book. I'm doing it on my own. But Landau will give you the same material, the same theorems, the same results. Landau will have everything. So whatever I'm doing is there in Landau, but in slightly different form. Okay?
But
so you have to do a little translation, that's all. Little translation. Okay?
So but anything near to your notation?
Yes, so maybe somewhat, there is some resemblance. I mean, I can't claim, because you see, Landau is Landau, and I'm I. So I can't claim to outsmart Landau, but there are some things which Landau does a little bit differently. And this difference will continue, because Landau does not do everything in electrodynamics in a completely Lorentz covariant way, which is what I'm trying to do. So the difference will continue to increase, and but on the other hand, everything we do you'll find some place in Landau, but you have to look for it. It's not done in the same sequence. It's not done in the same order, or even in the same notation, perhaps at times. But most of it is there in Landau.
So
Right?
that is creating the problem. Is
That
there
is
any,
no problem, Akshay. At your age, you are now going your third year, and you're getting to be you're taking these classes with MSc the students. So you will have to adjust to various sources with different notations. You see, when you read a paper, for instance, you have written a paper, right? A research paper which you've published, and you're given several references. Now, all these references have their own way of doing things, right?
yes, sir.
And you were able to translate between them and put everything in your own language, which is a very good effort. Your paper was excellent. And I would like everybody to do that. So don't expect, some Ramayana there and everybody will read Ramayana and everybody will know the same thing. That will not happen anymore. There are various books, but I'm absolutely certain about Landau. Landau's book is extraordinarily good. It's the best book on classical theory of physics. But there are other books also. So whatever book you use, I have no objection as long as you learn the subject. But I should go now because it's 11:32 and you have a class now. Okay? So thank you very much and bye bye. See you on Thursday at 10 o'clock.